in the past few years, podcasts have become increasingly popular, and leading the charge in podcasts is Spotify. Now, Spotify only very recently entered the market for podcasts in 2018. Despite that, in a few short years, so by 2021, they had already usurped Apple as the leader in terms of monthly active listeners. Now, Apple has been doing this for a very long time, since I think it's 2008 or maybe even earlier. But despite that, Spotify are now ahead of everyone. And of course, to back their sort of investments in podcasts, they've also invested heavily in the technology that powers different components of the podcast experience. Whether that's Anchor, which is an all-in-one app that allows people to record and publish podcasts, or what we're going to focus on, a natural language search for podcasts. Now, Spotify's natural language search or semantic search for podcasts is, I think, a really interesting use case because it enables a more intuitive user experience by allowing us to search through their podcast catalog, which is huge, using more natural language queries rather than the typical keyword or term matching that you would do in most places. So beforehand, where we were searching, we'd have to kind of know the words that we're looking for or the terms that we're looking for. And I think we as humans, we don't really know what exactly we're looking for in terms of the words or keywords that are in whatever it is we're looking for. Instead, we tend to think more in concepts and ideas. Our language is meaningful. It's not specifically about term matching or keyword matching. So it makes sense that we might want to create a search experience that replicates the meaning in language rather than just terms and words. So imagine we wanted to find a podcast that talks about eating healthily over the winter holidays. Okay, we might search something like this: we eat better during Xmas holidays. Now, in the dataset we're going to be using, there is a podcast description that talks about exactly this. Its description is: Alex Straney chats to Dr. Priya Alexander about how to stay healthy over Christmas and about her letter to patients. Now, if you compare those two, they don't share any of the same words, despite pretty much being about the same thing. So if you try and use this in a term matching query, it's not going to work. But if we were to swap that for a natural language query or a semantic search, it does, because what we are searching for here, the meaning overlaps. The genuine, human meaning behind those two phrases is very similar. And when semantic search is done properly, it is able to identify, okay, we're looking for the meaning behind these, and the meaning of these two does overlap. We're talking about sort of Christmas holidays, being healthy, eating better. They're very similar concepts. But enabling meaningful search in this way is not easy. So what I want to do is actually have a look at how Spotify have done this and actually replicate it and see what we can do as well. So the technology powering Spotify's semantic search consists of two different components. We have the NLP or natural language processing side of it, and we also have the vector search component. Now, these technologies can be seen as two steps in the search process. Given a natural language query, a language model, so this is the NLP side, will take that query and convert it into something we call a dense vector, which is essentially a meaning encoded numeric representation of whatever that query is. Okay, sounds confusing, but we'll see that it's not really too complex quite soon. These dense vectors can then be compared as you would compare normal vectors. So imagine you have 2 points in a particular space and you want to calculate the distance between them. We can literally do that, but with the meaning behind these queries. So let's have a look at an example of that. So here we just have a 3D chart, and typically when you have these dense vectors, they have many dimensions. Okay, so you're looking at sort of 700 plus dimensions in these vector representations. In this one, we've used PCA to reduce the dimensionality of those very high dimensional vectors into a 3D space, just so we can visualize it, but still maintain the sort of relationships between those vectors. So if we have a look here, we can see there's one main grouping of vectors. Okay, so these three over here. Now, let's just zoom in a little bit and have a look at what they are. So we have text podcasts about cooking and writing, a chat with chef who wrote books, and interview with cookbook author. So we can see that they're all about cooking and writing, and they've all been grouped together. Now, that's because our language model has taken these queries and encoded them in such a way that the vector representations for these represent the meaning. Okay, and the meaning of all of these, although it's not the same, is very similar, talking about cooking, writing, books, and so on. And we can see that represented in the proximity of these vectors. Now, let's have a look at something else that's kind of close, but not within that same cluster. So over here we have, how do I cook great food? Okay, so we're talking about cooking again. Okay, and then we have this one further over here, eat better during Xmas holidays. So we can kind of see that this one is, how do I cook great food? It's sort of in between like these about cooking and writing and a cookbook. And then over here, we have eat better during Christmas holidays. That's talking specifically about food. Okay, so this one is cooking and food, and it's in the middle of them both. And then we have a few more over here. And we have the writing show over here, so it's like a writing podcast or something. And then over here, one of the more similar vectors is how to tell more engaging stories. And then also how to keep readers interesting. So again, talking about writing. And then if we go up here, we see this is by itself, superhero film analysis. Obviously very different to everything else we've looked at. So this is kind of what I mean by representing the meaning numerically in a vector space. Similar things get grouped together, dissimilar things are separated. Now, all of those vectors have been encoded by a special kind of NLP model called a sentence transformer. Now, that sentence transformer is specially trained to do what we just saw, which is group similar things together, separate dissimilar things. Once we have those vectors from our sentence transformer, we need a way to compare them, and that's where the vector search component comes in. So imagine within all those queries that we just saw, imagine we came up with a new query, convert that query into a vector, place it within that vector space, and then we would search for the most similar other vectors, and we would return those as being the ones that are most similar to your particular query. Now, NLP and vector search have been around for a long time, but both fields have had very recent developments that have really acted as catalysts for the performance increases and subsequent adoption of semantic search. In NLP, we've had the introduction of transformer models, and in vector search, the introduction of ever better approximate nearest neighbor search algorithms. Now, transformers and approximate nearest neighbors have powered the growth of semantic search, but it's not inherently clear what both of those are. I'm assuming most of you probably have no idea what either of those are. If you do, then that's great. But otherwise, no problem, because we're going to actually go through both of those concepts as well. So starting with transformer models. Transformer models are essentially the standard in NLP now. They typically consist of two components, which is quite important for us to know. There's the core of the transformer, and then you usually have a head, which adapts the transformer for a particular task. Now, there's just one problem. The core of these transform models is huge. Like, they're massive models. And for most organizations, it is far too expensive to actually train the core of a model. For example, with BERT, which is one of the most popular language models, it's not even a particularly large language model. That costs were reported, I think, $2,500 to $50,000 to train a small one. And then when you look at the larger BERT model, that shifts up to $80,000 to $1.6 million, which is obviously huge. Now, most organizations don't have that kind of money lying around. So how do we, how are transformers useful for us if we can't afford to train them? Well, the way that we typically go about using transform models is, one, the core of a transform model is trained by the likes of Microsoft or Google. It costs them a lot of money to train it, but they have the money to do that. Two, the model is made publicly available by Microsoft or Google. Three, other organizations take this core, this transformer core, and they add different heads to it. So these heads are like a final few layers at the end of the model that adapt it for a particular task. Now, using that sort of extended model with the head, the model can be fine-tuned using a lot less computing power, which brings it within the range of feasibility for other more normal organizations. And four, once you've fine-tuned your extended transform model, you are able to go ahead and actually apply that to your specific task. So in the case of our example podcast search, we might want to take a BERT model. So like BERT based on case, which has been pre-trained by Google. We would take that and then we would add what's called a pooling head onto the end of it. That converts it into what we call sentence transformers, which will take an input like a normal transformer, so some sort of text input. The normal transformer will output a set of token level embeddings. Now, we can't use token level embeddings when we're comparing sentences because one token or one sentence for BERT can contain up to 512 tokens. So we really need a way to actually compress that down into one single vector to represent the full set of inputs that we've given to our transform model. So that's where we have that pooling layer. That pooling layer takes all of those token level embeddings and converts them into a single embedding, which is our sentence vector or sentence embedding. Now, there are different types of pooling layers, and we'll talk about one later, but they all consume the same input, and they all output that single embedding. And it is that sort of model that we would refer to as a sentence transformer. That sentence embedding at the end is what we referred to earlier as a dense vector, okay, the numerical representation of whatever we've fed into that transformer model. So given that dense vector, we move on to the next step, which is a vector search. Now, approximate nearest neighbors search allows us to search more efficiently through a lot of vectors, because in many use cases, for example, with Spotify, how many episodes do they have on there? I imagine there are many, okay? And it's very hard it takes a very long time if you compare like your query to all of the existing vector embeddings. It's very hard to do that quickly. Okay, in fact, it's impossible if you're using a typical k-nearest neighbors search, or otherwise known as exhaustive search, because you need to compare everything. And if you have millions of items to compare there, no matter what hardware you run, it's going to take a long time. So approximate search allows us to speed that up by literally approximating the answer. Now, approximate nearest neighbor algorithms are very good because they allow you to approximate the answer with a super high degree of accuracy, so like 99% accuracy, and make your search incredibly fast. You're talking sort of sub-second sub half a second. You're in the 10 millisecond range in a lot of cases. So that's really useful. But it's also worth noting that there is, between these different algorithms, there's usually a trade-off between speed, like your search times, and the accuracy. So you can have an even faster search, but then your accuracy will tend to be not quite as good. So you'll be returning maybe 70% accuracy rather than 99% accuracy. But there's always sort of a trade-off between the two. But generally, the algorithms now are very good, and you can get incredible accuracy and incredible speed as well. So we've merged those two together. We have our sentence transformers, we have our approximate search, and we now have a tool set that is capable of performing semantic search at incredibly large scales. So what I want to do now is look specifically at how Spotify did it. To build this kind of semantic search tool, Spotify first needed a model that can encode queries and episode metadata or descriptions into the same sort of vector space. Now, there are existing transform models or sentence transform models that can do a lot of things. For example, Expert. But Spotify found a few issues with those. Specifically for Expert, they needed a model that was capable of supporting multilingual queries, because obviously Spotify has a lot of content from every place in the world. So they couldn't use Expert because Expert has been trained on English-only data. And 2, Expert's performance on new domains, so for example podcasts, is not great without further fine-tuning. So the out-of-the-box, pre-trained, fine-tuned sentence BERT model could not be used. It didn't satisfy what Spotify needed. With that in mind, they decided to start with the pre-trained universal sentence encoder model. This allowed them to cover the multilingual issue, and yes, the USC model still needed to be fine-tuned, but they were going to need to do that anyway, so it's not really an issue. So let's have a look at what sort of data they use to actually fine-tune their model. So to fine-tune their model, Spotify needs query, episode pairs. Now, of course, Spotify has a ton of search logs over here. So they took these search logs and they used them to create 2 different data sources. The first was simply, okay, if there is a successful search, what was the query from that search and what was the episode? Okay, and that created this little data source that you see here. The other one's a bit more interesting. So whenever they found that there was a unsuccessful search that was straight away followed by a successful search, they looked at what the query for that unsuccessful search was, because the logic behind that being, if you're typing something, you're searching and it doesn't work, you probably use a more sort of natural language or a more natural feeling query. But then it doesn't work, so then you change it to be a bit more robotic and trying to fit what you would expect Spotify's search to come up with for the correct episode or podcast episode. So what they did is they took that unsuccessful search query and then the episode that the user found after their successful search and put them together to create this little data source. So we have 2 data sources. Now, we've used dotted lines here because we can't replicate that. We don't have Spotify's past search logs. So we will just ignore that, but we'll be aware that the way that they would be used would be exactly the same as this third data source over here, which we are going to replicate. Now, that third data source is taking podcast episodes, so it's a little diamond over here. We're transforming them. So what I mean by transforming is taking like the podcast show title and description and also the specific episode title and description and concatenating all of that together to create a sort of episode description from these multiple things. And then we use those sort of episodes, that episode data, with a query generation step. Now, query generation is super interesting. And what we're going to do there is actually use a query generation model to create synthetic queries for our episodes. And that will create this third data source over here, okay, which is synthetic queries to episode pairs. And we'll be using that. So we'll split that into sort of a training set, and we'll use that to fine tune a model in the same way that we would have used those the other two data sources. And we'll be fine tuning a pre-trained universal sentence encoder model. So we'll use all that. And in the end, what we'll have is this podcast universal sentence encoder model, which we can then use to encode both our queries and our episodes. So there's one other. So we have our podcast episodes over here, place them into this transform. We've created those podcast episode descriptions. This other data source that you see over here is a manually created data source. Spotify did this and they use it purely for evaluating the model. They didn't use this in training. So they just manually curated a set of queries for particular podcast episodes. We will do the same. We'll just do, I think it's like 7 queries and see how that works and use that to actually evaluate our model. Now, once we've done all of that, we come to the evaluation and also the actual, how you would use this. You would take your podcast model, you'd bring it over here into the middle here, and then you're going to take the evaluation data from your query generated data, bring it into here. You're going to encode everything and place it into a vector search engine. In this case, we're using Pinecone. This will allow us to store all of our episodes as embeddings, and then we'll be able to query and see if we are returning the correct episode based on our synthetic queries to episode pairs. And we'll also do the same using these manually curated query episode pairs. And then this is exactly what you would do in production as well. So after you've evaluated, you take all of your episode embeddings, put them in your vector database, so the Pinecone at the bottom there, and then you would let your users query. Your query would go into your podcast sentence transform model, and then it would be passed into your vector database, which would identify the most semantically similar or most relevant episode vectors for you. Okay, so that's very high level. That's how it all works. If it's confusing, no problem, because we're going to work through all of this. So now we'll move on to the actual implementation of all of this. Now, what we first want is a data set that is going to, as closely as possible, replicate the episode data that Spotify are using. So we'll need Kaggle for this. So you can download or install the Kaggle API using pip install Kaggle. And then you'll need an account. So you need to sign up on kaggle.com and you can get an API key. So you just come over here, you click on top right, you'll see your sort of profile. You go to, I think, account, and you can come down and you have API here. So you'll be able to get, create a new API token, and it will download a kaggle.json file for you. And then what you do with that is if you try to import Kaggle, so you run this import Kaggle, it will say, okay, you are not authenticated because you don't have kaggle.json in this directory. So all you do is put your kaggle.json in the directory that's specified. Once you've done that, you should be able to import Kaggle without any errors. And we'll move on to the data download. So we just authenticate our API. I'm not going to go too into depth here. There will be a link to this notebook so you can read through everything as you want. And all we're going to do is download these 2 data sets. Okay, so let me copy this and I'll show you on Kaggle this data set. Okay, so it says all podcast episodes published in December 2017 from this company called Listen Notes, which is a podcast search engine. So we download these podcasts and episodes data and we extract them because they'll be in zip files. And we can see, okay, this podcast is actually the details of the podcast show itself. And episodes is the details of this, individual episodes. And what Spotify did was concatenate the title and description from both of those and use that to create a sort of a single episode description that we then encode. So we do the same. We first need to merge those two data frames. So we're doing that based on the unique podcast ID, and we get this sort of data frame with everything we need inside it. I'm just doing a little bit of data cleaning here, so stripping any white space from the features that we care about. So the title EP, description EP, title podcast, and description podcast. EP here is just episode. And then I'm also just removing, where we have any null values in any of those columns or features, just removing them. Because we have a lot here anyway, we don't even use all of these. So it's not a problem. And then I'm concatenating everything. I'm just putting a full stop in between each one of them. And then converting that into a list. So we just have like a list of these episode texts now. Okay. And you see they do vary a lot. It's not the cleanest data, but it's usable. We also shuffle here as well. When you're shuffling, just bear in mind your shuffle is going to randomize the order. So later on, when we have these curated queries, they won't necessarily be in the test set for you as well. So you may need to just make up some new queries. And at that point, we have our episodes data, and we need to move on to query generation because we need query episode pairs. So Spotify use they fine-tuned a BART model on MS Marco. Now, I'm not going to fine-tune a model because there are honestly so many query generation models that have been fine-tuned on MS Marco already, including BART models. So I don't think there's really any point in us fine-tuning it because we're just replicating what we can just pull from Hugging Face Hub. I tested a few different BART and T5 query generation models, and I found this one to be the best for this particular use case. The queries were just more consistently sensical, like they actually made sense. And it also supports it has some multilingual support. I'm not sure how much, but it does manage to actually produce queries that make sense in different languages. So that's definitely pretty useful and aligns pretty nicely with what Spotify wanted as well. And then all I'm doing is, I'm using the transformers library, so it's Hugging Face transformers. You can pip install transformers if you need to. I'm just initializing the tokenizer and the model. Okay, so this is going to handle our query generation. On the end here, you see I put CUDA. That's because I have a CUDA enabled GPU, which will make things a lot faster when we're doing this, because this can take a long time. And that's why I'm just taking the first 100,000 episodes here. So we move on to the query generation loop. It's fairly long, sorry. This is like the quickest way you can do it. So larger batch size means faster processing, but this is limited by the size of your GPU. And then number of queries that I'm generating for each episode. So Spotify didn't specify what they use for number of queries here, but I'm using 3 because that's in line with the approach taken by these other query generation techniques, GenQ and GPL. So I'm going to stick with that. Then we're just going through encoding everything in batches. So we're just tokenizing everything, and then we're generating 3 queries per episode. Decoding those queries back to human readable text, because this just outputs a load of token IDs, numbers. Decoding them back to text, and then looping through and putting all those together. So the query and episode pairs and placing those together. Synthetic queries and episode pairs. Okay, and then we put all those in this pairs list. Okay, and we can see a few here. So we have like a query, and then we have an episode, node query, episode, and so on. You can also see, so here we have the multilingual support as well, which is really cool. And also again here. So we now have a data source that we can use for fine-tuning the model. Spotify talk about this in their article, which is here. And they mention that they tried, here. So they tried BERT, but as I said, they decided they didn't really like it. So, we're not using it for these multiple reasons that I mentioned before. So what they did is use this universal sentence encoder model. And we're going to do something similar, but what I will note here is that they use TensorFlow Hub. And we can use TensorFlow Hub, but it means we can't be stuck with TensorFlow, and it makes our lives harder rather than using Hugging Face and PyTorch and the Sentence Transformers library. So rather than using the universal sentence encoder model, which we can't get from the Sentence Transformers library as a pre-trained model, we are going to use a distilled universal sentence encoder model, which is literally like a smaller version of USE. So we'll come down here and we're using this one here. So distilled USE based multilingual case. Okay. So it's good, it's multilingual, and it's still pretty much the same model as what Spotify used. So we just have the model details here. So the maximum number of tokens it will accept is 128, and it will output a 768 dimensional dense vector. So that's the meaningful vector that we spoke about earlier. Now, when we're fine-tuning with the Sentence Transformers library, and by the way, if you do need to install that, you can just go pip install Sentence Transformers like this. Okay, obviously in your terminal or using the exclamation mark at the start there. So when we're using Sentence Transformers library and we're fine-tuning a model, we need to reformat our data, our input data, so our pairs, into a list of input example objects. Now, this input example object, the format for that varies depending on what task you're actually fine-tuning with. Now, we're using a ranking task for fine-tuning or optimizing our model, and that means that we only need the query and the episode. Okay, so all we do in that case, so I'm here as well, I'm just splitting, so we have an evaluation set down here and a test set as well for later on when we're evaluating things. So all we need in our input example, which we have imported from Sentence Transformers, is the query and episode. It's literally it. So it's just a list of these input examples with query and episode in there. And you see the sample sizes that we have there. So let's continue, and so as I mentioned, we're going to be using a ranking optimization function. Now, what does that look like? Given a specific query, like the one we used earlier, so eat better during Christmas holidays or Xmas holidays, our model is going to be given a set of episodes, and it's going to need to rank the true episode for that particular query as number one in terms of scores. Okay, so the true sort of pair for this query is this one here, and it will have to be able to identify that all these other episodes are not real pairs or are less semantically similar to this particular query. So the model learns to give higher scores to more semantically similar episodes for a particular query and lower scores to the more dissimilar episodes for a particular query. And that's why we don't need like a label in this case. We don't actually need a particular similarity label or anything when training our model, which is a really nice sort of benefit of using ranking functions. You literally just need pairs of data and you can train with that, which is pretty cool. Now, the way the model actually needs to compare the queries and episodes is by taking a query, converting it into a query vector, taking the episode, converting that into a episode vector, and placing them in a vector space and comparing the similarity between them. Now, the way that we are going to be calculating similarity in this case is using cosine similarity. So we're essentially calculating the similarity or the angle between vectors. So this in the middle here, that is our query vector. And this little cone is representing the angle in a 3D space around that query vector. These two episode vectors here, or episode embeddings, are the two most similar. So we've got top k equals 2 over here. That's because we're trying to return the two most similar. And these other vectors, like this one, for example, in terms of actual distance, this one might actually be closer than this one. But in terms of angular distance, it's further away. So that's why we have these two embeddings being selected rather than any of these other ones. So the model needs to create these vectors, and it needs to learn how to put similar meaning querying episodes in a similar vector space, and dissimilar querying episodes in as far apart as possible. Now, another thing that we need to consider here is, because we're using a ranking function, which is going to work by taking a query and then a batch of episodes, we need to make sure that within that batch of episodes, we don't have any duplicates. Because imagine, so we're going to be optimizing this model, and we've got a query and episode pair, and we're saying, okay, for this query, this episode is the most similar, and we're going to optimizing the model based on that. If we have the exact same episode further down in that list, and we're telling the model, actually, okay, these two episodes are exactly the same, but one is right and one is not, our model's just going to be confused. That doesn't make sense. It can't do that. So we have to make sure that we don't have duplicates in any of the training batches. Now, it's probably not a problem if you have the odd one, but we don't want any. We just want to be certain there's nothing in there. So we can actually do that using Sentence Transformer's no duplicates data loader, which will handle removing any duplicates from batches for us. As well, we use a batch size of 64. So if we consider the training optimization function here, we're taking query and then we're taking a batch of episodes. Imagine we have a batch size of 3, right? Or even 2. We have a batch size of 2. We're just comparing our one query against 2 episodes. Our model can get even if it's just randomly guessing, it can get the right answer around 50% of the time with such a small batch size. If we increase that to 100, then the model is going to perform a lot more poorly randomly guessing. So the consequence of that is that using a larger batch size for this particular training method is going to typically result in you having a better performing model, because it makes the task of ranking harder for the model. So your model must get better in order to actually accurately rank everything. So we increase the batch size as much as our hardware will allow us to. Now, after that, we can initialize the loss function. This is where the ranking optimization comes in. So in Sentence Transformers, the ranking function is its multiple negatives ranking loss. Okay, so we initialize that. There is just one more step before we actually move on to fine tuning. So if we have a look over here and we go down to offline evaluation. In order to evaluate the model, they use 2 different types of metrics, in-batch metrics and full retrieval. We're going to do both. So for the in-batch metrics, so just calculating recall and MMR at the batch level. Okay, so what we can do to replicate that is use this re-ranking evaluator from Sentence Transformers, and we use that to perform ranking and calculate the MMR metric using our evaluation set. So just one thing, as we have already done here, is we've removed duplicates from batches. We need to do the same before we actually feed data into our re-ranking evaluator. Remember, there are a lot because we created 3 queries per episode, so we definitely do need to remove those. So we remove any duplicates using this, and in the end we have 1,000 unique pairs for our evaluation set. So then we feed them into the re-ranking evaluator, which requires a particular format of query, a any positives we have. So we just have one positive per query here. So it's just a single list, and then negative. And then in here, we just need to pass in all of the other episodes that are not the positive episode for that particular query. So we do that in here, and then we initialize the re-ranking evaluator, and I set MMR at K to consider the top 5 items when it's calculating its score. I'm not going to go into the metrics because it takes a little bit more time. So calculating the performance, so this is the MMR at 5 for the model without any fine tuning. So we get 0.68. Okay, so at this point we're actually ready to go ahead and fine tune our model, and this is basically the easiest step. So we set the number of epochs to 1. I did try other, so like more epochs. Typically with sentence transformers, you actually only really need to train for 1 epoch, depending on the model and the data. Anything more, it actually degraded the performance. So it went 1 epoch here, and we always or typically use a number of warm-up steps. So here, for the first 10% of training steps, the learning rate is going to be slowly increasing up to the default learning rate, which I think is like 1e to the -5 or something along those lines. And then we're just saving the model that we train into this directory here. So distill USE podcast NQ. NQ here is like natural query. And then, yeah, so that trains. It shouldn't take too long. I think maybe this took an hour, maybe 2 hours to train. So it's pretty quick. And with that, we can actually look at the evaluation. So, how did this model perform on the evaluator that we initialized at the start? And we can actually see that. So I'm in another environment here where I actually trained the model. We go to this distill USE podcast NQ folder, and then here we'll see this eval directory. Go in here, open this, and we can see we have over on the right here the MMR at 5 value, and it's 0.888. So that is a big improvement from what we had up here, which is 0.68. So it's a 20-point increase, which is really good. That's on small batches, so that doesn't really replicate the real world use of this model. So what we want to do in the final evaluation step is replicate that. So what we're going to do is take the test data we had, which has many thousands of episodes in there. We're going to encode all of those, and then we're going to perform a semantic search as we would expect this to be used in real life. So what we'll do is set up the vector database with thousands of episode vectors in there from our test data set, and then we're going to calculate the recall value this time for our fine-tuned model and also our not fine-tuned model. So we initialize Pinecone, create a evaluation index here, make sure we use the cosine metric. We connect to that. Oh, if you need an API key, you need to go to app.pinecone.io. It's free, so this is all free. There's nothing, you don't need to worry about anything there. We create our index, we connect to it here. And then what we can do is, so before we index our test data, we remove duplicates like we did with the evaluation set earlier. Same thing, I'm not going to go through it again. And then here, so what I'm doing is going through, again, just make sure there's definitely no duplicates in there. There shouldn't be anyway, but just in case, we're going through and creating batches of episodes to actually encode here using our new model. This is using the distill USE podcast NQ model. And then we insert them into our Pinecone vector database, and then just refreshing the batch and doing it again, all in batches. And then at the end here, I'm just having a look at the index stats so we can see how many vectors we actually have in there, which is 18,500. Then what I'm doing here is I'm going to calculate the recall at k. So I'm going to loop through all of the queries we have. So all the queries from our test set. So these are synthetic queries first. And just looking at, okay, what is the recall using those synthetic queries? Now, it's 0.88, which is like incredibly good, but we're using synthetic queries here. So it's not really representative of real, like human queries. So this is where the curated queries come in. So I went through, I found different episode descriptions, which were in the indexes 1, 8, 14, and so on. And I just created like a query for each one of those episodes. That makes sense to me. Okay. Now, this isn't perfectly accurate. That we could use this and we could return another episode that's actually more relevant. But using what I've done here, it would show up as not a match and bring down the score. So just bear that in mind as well. So once we use those curated, like true query episode pairs or more sort of human queries, we get a recall at k of 57. Now, it doesn't, like, it's definitely not as impressive as the 88 we had before. It's okay, but it's nothing special. But what I want to do here is just compare this to what we had before, so the pre-trained model without any fine-tuning. Okay, so to do that, I'm just creating a new index. If you're using the free version of Pinecone, you can only have one index at a time, so you will have to, you can delete an index, so you can then refresh it and do this. So what we do is I'm going to initialize the pre-trained model that hasn't been fine-tuned on our particular data set. And here I am creating a new index, eval 0, connecting to that index, and then I'm going through doing the exact same thing as I did before. Okay, so just pushing all of those vectors or episode embeddings that have been encoded using the older model that hasn't been fine-tuned, and then calculating the recall at k again using that, using the curated dataset, and we get a terrible score of 0.28. So we can see there's actually a massive improvement from 28 to 57. That's a 29-point improvement, which is huge, especially to say that our training data was synthetic, right? So it's a synthetic data set is never going to perform as well as a genuine data set. So if we had those other two data sources that Spotify used, we could probably create something that is like very impressive compared to what we've done here. But to say we've just used episode data without any queries and synthetically created queries, I think this is really impressive. And it shows that Spotify's methodology, at least in terms of adding these synthetic queries in, definitely does contribute to their overall model. And it shows us a really cool way to, without any real training data, do this. Now, another thing that we should really think about here is how well does this scale? So we're only using 18,500 vectors in this like evaluation case. Using Pinecone, we're quite easily able to go up to hundreds of millions of episodes or vectors in there, and even billions. So in terms of scalability, that is, well, unless you're going into the sort of trillion scale, this is very possible with pretty much every data set that you're going to be using. And it will still be incredibly fast, which is I think, really cool. I think, that's really awesome, the fact that we can do this. No data, make it incredibly scalable, and, build something really, really awesome. So that's it for this sort of walkthrough. I will say, just if you are going to build something like this with Pinecone and doing all this sort of cool vector search stuff, let me know, because over at Pinecone we are looking for people that would like to showcase the work that they're doing, and it would be really cool to see what you're building, and if you'd sort of like to share that and get other people seeing what you're building, I think that's a really good way to do that. So if you're interested in that, just go over to the community page at Pinecone and you'll be able to find how to submit any projects that you're working on there. So I hope all this has been useful and interesting. Thank you very much for watching, and I will see you again in the next one. Bye.